In part 4 of load switch design, we'll take a look at what happens when the load is capacitive. This is when the design gets a little more interesting and challenging. You can split up any electronic load into one of three categories: resistive, capacitive, or inductive. There's some real-life examples of these types of loads listed here. The classic resistive load is a heater. LEDs themselves aren't resistive, but since they usually include a current-limiting resistor, they end up behaving pretty similarly to a resistive load from the perspective of a load switch. One of the most common types of load is capacitive. For example, FPGAs and microcontroller designs include a substantial amount of decoupling capacitors, making them look like a capacitive load overall. Anything involving power regulation or conversion will also have a lot of front-end capacitance. Inductive loads are also common. Relays, motors, and solenoids are typical examples. While resistive loads don't present any particular challenges, capacitive loads will stress switches during turn-on, and inductive loads will stress load switches on turn-off. The main issue with capacitive loads is that load switches by design create a fast dV/dt transition at the output. The capacitor equation tells us that this will in turn create a large inrush proportional to the voltage slew rate and the capacitance of the load. For the load switch we've designed so far and the 500 microfarad load, the spike hits 15 amps of current every time the switch is turned on. Uncontrolled inrush will stress the switch itself and can also cause upstream problems on the power bus. The input voltage can droop, affecting other devices, or even trigger undervoltage responses. It's not great for noise either. It helps to see that the source, gate, and drain nodes of a FET have inherent capacitors from the device's silicon structure. The fact that these capacitors exist means that they will have to be charged and discharged as the FET turns on and off, so turn on and turn off is not instant. The value of these capacitors is given in the dynamic characteristics section of the datasheet as CISS, COSS, and CRSS. You can convert the datasheet capacitances given into the FET's gate-to-source, drain-to-source, and gate-to-drain capacitances. Note that the CGD capacitance is around 100 picofarads. We'll use this later. We'll also use the nominal gate threshold voltage, which is 1.5 volts. So here's the technique to limit inrush. C limit is added between the gate and drain, and R limit is added between the gate and the collector of the enable switch. As the switch starts to turn on, the drain voltage, or the output, starts to rise. The gate voltage during this transition is nearly constant, and as drain voltage changes from 0 to 5 volts, C limit has to charge up, and the only available current path is through R limit. So from the capacitor equation, IC equals C dV/dt, we have control over C, that's the C limit capacitor. dV is known, that's the rise from 0 to 5 volts. IC is controlled via R limit, it's the gate voltage over the R limit resistor. The current path is shown with the yellow arrow. The only thing left is dt. This is the time during which the output voltage changes from 0 to 5 volts, which we deliberately slow down to limit the inrush. Once we know the time, we can also compute the current that will flow into the capacitive load, once again using the capacitor equation. Let's take a look at how to choose the appropriate time period for inrush control. The main concern here is protecting the pass switch by limiting the stress it will see. The FET's energy is a good metric to use for this, and it will equal the sum of the energy used to get 5 volts across the capacitor and the resistor of the load. Let's take a look at the resistor portion first. The plot shows the voltage change across the FET as it turns on, dropping from Vin to 0 volts. The current through the resistive load rises at the same time. So you can get power of the MOSFET using voltage times current. Then energy is power multiplied by time, or the integral of power over time. The functions for voltage across the FET, the resistor current, and the drain voltage are shown. The source voltage is the input voltage. Plugging everything into the integral and simplifying gets it to this form. The solution to the integral is the product of 1/6 the input voltage, the final load current across the resistor, and the time limit. For the capacitor, the energy is just the capacitor energy formula, 1/2 CV squared. The sum of these two functions gives the energy across the MOSFET. Next, we need to find the energy limit for the part. There's a plot in the datasheet that can be used for this. It gives a factor that can be used to adjust the thermal resistance theta JA, which we talked about in part 3. We'll adjust the thermal resistance for the time period that the transistor is used to limit inrush current. To make things slightly simpler, let's assume we know that there's a microcontroller requirement where the load switch enable command can only be sent once per second at most, so the switch can't be turned on and off hundreds of times per second. In this case, the single pulse curve is the one to use. The red lines were added as measurements of the single pulse line. This is done just by taking a screenshot of the datasheet graph and adding red lines in PowerPoint. The green line is added and used as the reference. The table shows post duration times in the first column and the length of the red lines in inch in the second column. You can just read off the length of the line in PowerPoint in the Format Shape sidebar. The formula for converting the length in inch back to the scale of the graph in the datasheets is shown. The green reference line is the length of 1 decade in the y-axis, so using its length in inch allows the conversion to work out. Using RT, the power that the part can handle for the brief duration is computed. The 20-degree delta T is based on the ambient and junction temperature difference from the requirements. Finally, the energy limit is the post duration multiplied by power. A nice way to use this information is to create a graph in Excel. Take the energy of the FET, which we figured out a couple of minutes ago, and plot it against the energy limit that was just computed. You can do the same thing just using the table as well. Column 4 is the energy margin, or how much breathing room there is. You can see that 1 to 3 milliseconds is the sweet spot for this part. The last column shows the expected capacitive load current during startup, since we need to make sure that's reasonable too, and it is. Inrush, that's 2x the steady state, is very reasonable. It's worth noting that the energy of the FET has a direct relationship with the load capacitance. A larger capacitive load would require changing the package of the FET to improve thermal performance. So back to what we were doing, trying to figure out the output voltage rise time, or T limit. To keep the MOSFET safe, we'll use 2 milliseconds for the rise time. So 2 parts are in our control, the limit resistor and capacitor. Earlier we saw that CGD of the transistor itself is about 100 picofarads. This value is really an estimate, and in reality, the capacitance of the MOSFET is nonlinear and changes as it's charged up and down. To avoid this and keep the ramp rate linear, it helps to choose a much larger C limit compared to CGD, so let's make it at least 100x. We'll go a little beyond that and choose a very common cap value, 0.1 microfarads. Then we can compute R limit just by plugging in the values. This means that the charging current for C limit will be Vg over R limit, or about 250 microamps. Plugging this into our sim gives the plots shown. In LTSpice, once the sim runs, you can Alt left click on the transistor to plot its power waveform. Once the power waveform is available, you can zoom into the relevant area and Control left click on the name of the power waveform to get a pop-up window that tells you the average power and the integral of power, which is the energy. These 2 calculations are done over the visible plot, so it's important to zoom in to the proper location. Since we can get all of this info, we can check how close the calculated design values are to the sim. T limit in the sim ended up being 0.3 milliseconds higher than calculated, 2.3 versus 2 milliseconds. The energy of the MOSFET is right between the numbers calculated for 2 milliseconds and 3 milliseconds, so that seems okay. The C load current is a little bit lower, but that makes sense since the time limit is higher, so the energy is more spread out. The reason for the difference is that we used 1.5 volts for the source to gate voltage, which was the nominal given in the datasheet. The sim source to gate voltage can be seen on the plot, and it's actually slightly over 2 volts. Since the gate voltage and R limit are what set the C limit charging current, that explains the difference. There's not really a reason to adjust this, as variation in the gate voltage should be expected. There will naturally be differences in these values due to part variation, temperature, or other factors. Worst case analysis can be used on something like this to ensure that the part is always safe. If it didn't pass, we'd have to choose a different package or lower the capacitance of the load. The last thing to look at is the turn-off of the switch. R limit works both ways, and actually during turn-off, the current is limited by both the pull-up resistor, R2, and R limit, so the fall time would be slower than the rise time. To avoid this, a way to bypass the resistance is required. Adding an NPN transistor between the source and gate of the load switch allows for a discharge path to form during turn-off, quickly discharging C limit. The before and after plots show the difference that this new BJT makes in the current flow turn-off. Here's the final look at the controlled inrush load switch design, with waveforms for the drain voltage and FET current shown.